Section 35 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Frequently asked questions: climate, weather, and extreme events. Question: was there a hiatus in global warming? Short answer: temperature records show that the long-term, 30 years or longer, trend in increasing surface temperatures has not ceased. The rate of warming has been faster during some decades and slower during others, but these relatively short periods of time are not the basis for scientists' conclusion that sustained global warming is occurring. Long answer: global warming refers to the increase in global average surface temperature that has been observed for more than a century. This warming is clearly revealed in both the surface temperature record and in satellite measurements of lower atmospheric troposphere temperature. While the long-term trend shows warming, scientists expect that the rate of warming will vary from year to year or decade to decade due to the variability inherent in the climate system, or due to short-term changes in climate forcings, such as aerosols, dust, pollution, or volcanic particles, or incoming solar energy, figure A5.18. Temporary slowdowns in the rate of warming have occurred earlier in the historical record, even as carbon dioxide concentrations continued to rise. Temporary speed-ups have also occurred, most notably from the early 1900s to the 1940s, and from the 1970s to the late 1990s. Computer simulations of both historical and future climate produce similar variations in the rate of warming, making recent variations in short-term temperature trends unsurprising. From the mid-1940s to the mid-1970s, there was almost no increase in global temperature, possibly related to an increase in volcanic activity and/or human-caused aerosol emissions. Most notably, for the 15 years following the 1997 through 1998 El Niño event, the observed rate of temperature increase was smaller than what was projected by some climate models. However, during this period, other indicators of climate change continued previous trends associated with warming, such as increasing ocean heat content and decreasing Arctic sea ice extent. Figure A5.19. See Wobbles et al. 2017, Box 1.1. Question: what is an extreme event? Short answer: an extreme event is a weather or climate-related event that is particularly rare for a given time of year and location. These events include drought, wildfires, floods, severe storms, including hurricanes, heat waves, cold snaps, and heavy rains, and they can have devastating impacts on local communities, infrastructure, the economy, and the environment. Long answer: scientists determine if an event is extreme or not by comparing measurements of weather and climate variables, rainfall, wind speed, temperature, etc., with thresholds. Events above or below these thresholds are considered rare occurrences, such as events that rank in the highest or lowest 5% of observed values. Several thresholds may be used to define if a single event is considered extreme, and the threshold may change depending on the period of interest, day, month, season, year, etc., and the chosen reference period, for example, 1961 through 1990 versus 1900 through 2000. It is possible for a single event to meet the definition of an extreme event, but not have a large impact. Conversely, it is possible for several types of events that may not be considered extreme individually to cause catastrophic impacts when taken together, such as a sequence of hot days that occur during dry conditions that worsen a drought, or several rainfall events occurring one after another that produce flooding. See Wobbles et al. 2017, Knudsen et al. 2017, and Kosen et al. 2017 for more detail on extreme events. Question: have there been changes in extreme weather events? Short answer: yes. Climate change can and has altered the frequency, intensity, duration, or timing of certain types of extreme weather events when compared to past time periods. The harmful effects of severe weather raise concerns about how climate change might alter the risk of such events. Long answer: while there have always been extreme events due to natural causes, the frequency and severity of some types of events have increased due to climate change. Figure A5.20. See also Chapter 2, Climate. As average temperatures have warmed due to emissions of greenhouse gases, GHGs, from human activities, extreme high temperatures have become more frequent and extreme cold temperatures less frequent. From 2001 to 2012, more than twice as many daily high temperature records, as compared to low temperature records, were broken in the United States. With continued increases in the level of GHGs in the atmosphere, the chances for extreme high temperature will continue to increase, with the occurrence of extreme low temperatures becoming less common. Even with much warmer average temperatures later in the century, there may still be occasional record cold snaps, though occurrences of record heat will be more common. Because warmer air can hold more moisture, heavy rainfall events have become more frequent and severe in some areas, and are projected to increase in frequency and severity as the world continues to warm. Both the intensity and rainfall rates of Atlantic hurricanes are projected to increase. See, for example, Chapter 2, Climate, Box 2.5, with the strongest storms getting stronger in a warming climate. Recent research has shown how global warming can alter atmospheric circulation and weather patterns, such as the jet stream, affecting the location, frequency, and duration of these and other extremes. More research would be required to improve scientific understanding of how human-caused climate change will affect other types of extreme weather events important to the United States, such as tornadoes and severe thunderstorms. These events occur over much smaller scales of time and space, which makes observations and modeling more challenging. Projecting the future influence of climate change on these events can also be complicated by the fact that some of the risk factors for these events may increase, while others may decrease. Question: can specific weather or climate-related events be attributed to climate change? Short answer: while it is difficult to attribute a specific weather or climate-related event to any one cause, climate change can affect whether an event was more or less likely to occur. Climate change can also influence the severity of these events. Our ability to detect the influence of human-caused warming on particular kinds of extreme events depends both on the length and quality of our historical records of those events, as well as how well we can simulate the environmental processes that produce and sustain them. Long answer. Extreme event attribution is a relatively recent scientific advancement that seeks to determine whether climate change altered the likelihood of occurrence of a given extreme event. A long-term, high-quality record of a given type of event and a computer model capable of producing a realistic simulation of the event are needed in order to assess the influence of climate change. Because of these data and modeling constraints, our ability to detect the influence of human-caused global warming on heat waves and, to a lesser extent, heavy rainfall events is better at present than our ability to detect its influence on tornadoes or hurricanes. As scientists collect more data and develop more advanced tools, they will be able to better quantify cause and effect relationships in the climate system, which should improve their ability to attribute how much human-caused climate change contributes to specific weather and climate-related events. One example of event attribution comes from the recent California drought, where scientists found that human-caused climate change contributed 8% to 27% to the severity of the drought. Droughts are frequent in the Southwest and occur regardless of human activity, but human-caused climate change leads to increased evaporation and decreased soil moisture, intensifying droughts during periods of little rain. Question: could climate change make Atlantic hurricanes worse? Short answer. Atlantic hurricane activity has increased since the 1970s, but the relatively short length of high-quality hurricane records does not yet allow us to say how much of that increase is natural and how much may be due to human activity. With future warming, hurricane rainfall rates are likely to increase, as will the number of very intense hurricanes, according to both theory and numerical models. However, models disagree about whether the total number of Atlantic hurricanes will increase or decrease. Rising sea level will increase the threat of storm surge flooding during hurricanes. Long answer. Hurricane activity is undeniably linked to sea surface temperatures. See Chapter 2 Climate, Box 2.5 for a discussion on the 2017 Atlantic hurricane season. Other influences being equal, warmer waters yield stronger hurricanes with heavier rainfall. The tropical Atlantic Ocean has warmed over the past century, at least partly due to human-caused emissions of greenhouse gases. However, high-quality records of Atlantic hurricanes are too short to reliably separate any long-term trends in hurricane frequency, intensity, storm surge, or rainfall rates from natural variability. This does not mean that no trends exist, only that the data record is not long enough to determine the cause. Most models agree that climate change through the 21st century is likely to increase the average intensity and rainfall rates of hurricanes in the Atlantic and other basins. Models are less certain about whether the average number of storms per season will increase or decrease. Early modeling raised the possibility of a significant future increase in the number of Category 4 and 5 storms in the Atlantic, figure A5.21. While that remains possible, the most recent high-resolution modeling provides mixed messages. Some models project increases in the number of the basin's strongest storms, and others project decreases. Regardless of any human-influenced changes in storm frequency or intensity, Rising sea level will increase the threat of storm surge flooding during hurricanes. Chapter 8 Coastal, Chapter 18 Northeast, Chapter 19 Southeast, Chapter 20 U.S. Caribbean, Chapter 23 Southern Great Plains. End of section 35. Section 36 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Frequently asked questions. Societal effects. Question: how is climate change affecting society? Short answer: climate change is altering the world around us in ways that become increasingly evident with each passing decade. Natural and human systems that we rely on are being impacted by more intense precipitation events, rising sea level, and a warming ocean, and will be impacted by projected increases in the frequency of droughts and heat waves and other extreme weather patterns. Long answer: many people are already being affected by the changes that are occurring, and more will be affected as these changes continue to unfold. Figure A5.22. In the Northeast and Northwest, fishing communities have to adapt to increasing ocean temperatures and acidification that impact fish and shellfish. Chapter 9 Oceans, Chapter 18 Northeast, Chapter 24 Northwest. Coastal communities, especially those located on islands, will need to confront rising sea levels, which are already contaminating freshwater supplies, flooding streets during high tides, and exacerbating storm surge flooding. Chapter 8 Coastal, Chapter 19 Southeast, Chapter 20 U.S. Caribbean, Chapter 27 Hawaii and Pacific Islands. Shifts in the timing of the seasons and changes in the location of plants and animals affect communities dependent on those resources for tourism, economy, and/or cultural purposes. Chapter 7 Ecosystems, Chapter 15 Tribes, Chapter 26 Alaska. Changes are not only happening in the oceans and along the coast. Farmers, the livestock they tend, and other outdoor laborers are expected to be adversely affected by warmer temperatures and increasing frequency of heat waves and an increasing number of warm nights. Chapter 10 Ag and Rural, Chapter 14 Human Health, Chapter 19 Southeast, Chapter 23 Southern Great Plains. Some communities may have to adapt to both an increase in the frequency of drought and more rain falling as heavy precipitation, while deteriorating water infrastructure compounds those risks. Chapter 3 Water, Chapter 17 Complex Systems, Chapter 22 Northern Great Plains, Chapter 25 Southwest. The geographic range and distribution of some pests and pathogens are projected to change in some regions, exposing livestock and crops to new or additional stressors and exposing more people to diseases transmitted by those pests. Chapter 14 Human Health, Chapter 21 Midwest. Infrastructure across the country, which supports economic activity, is increasingly being tested and impacted by climate change, including airport runways affected by increased surface temperature and coastal streets inundated by high tide flooding. Chapter 12 Transportation. Much of the current built environment throughout the country has been developed based on the assumption that future climate will be similar to that of the past, which is no longer a valid assumption. Chapter 11 Urban. In general, the larger and faster the changes in climate, the more difficult it is for human and natural systems to adapt. Adaptation efforts not only help communities become more resilient, they may also create new jobs and help stimulate local economies. See frequently asked question, what are climate change mitigation, adaptation, and resilience? Question, what is the social cost of carbon? Short answer, the social cost of carbon is an estimate of the monetary value of the cumulative damages caused by long-term climate change due to an additional amount of carbon dioxide, CO2, emitted. This value quantifies the potential benefits of a reduction in CO2 emissions. Long answer. The social cost of carbon, SCC, includes the economic costs of climate change that will be felt in market sectors such as agriculture, energy services, and coastal resources, as well as non-market impacts on human health and ecosystems, to name a few. SCC values are computed by simulating the causal chain from greenhouse gas emissions to physical climate change to climate damages in order to estimate the additional damages over time incurred from an additional metric ton of CO2. This value can be used to inform climate risk management decisions at national, state, and corporate levels, as well as in regulatory impact analysis to evaluate benefits of marginal CO2 reductions. For example, in rules affecting appliance efficiency, power generation, industry, and transportation, such as the benefits of increased vehicle gas mileage standards. As with many complex interacting systems, it is challenging to develop comprehensive SCC estimates, but this is an active area of research guided by recent recommendations from the National Academies of Sciences, Engineering, and Medicine to keep up with the current state of scientific knowledge, better characterize key uncertainties, and improve transparency. Notably, estimating the SCC depends on normative social values such as time preference, risk aversion, and equity considerations that can lead to a range of values. Ongoing interdisciplinary collaborations and research findings from the climate change impacts, adaptation, and vulnerability literature, including those discussed in the Fourth National Climate Assessment, are being used to improve the robustness of climate damage quantification and, thus, SCC estimates. Question: what are climate change mitigation, adaptation, and resilience? Short answer: mitigation, adaptation, and resilience are related but different terms in the context of climate change. Mitigation refers to actions that reduce the amount and speed of future climate change by reducing emissions of greenhouse gases, GHGs, or removing carbon dioxide from the atmosphere. Adaptation refers to adjustments in natural or human systems in response to a new or changing environment that exploit beneficial opportunities or moderate negative effects. Thus, adaptation is closely related to resilience, which is the capacity to prevent, withstand, respond to, and recover from a disruption with minimum damage to social well-being, the economy, and the environment. Long answer: mitigation efforts can reduce emissions or increase storage of GHGs. For example, shifting from fossil fuels to low-carbon energy sources will generally result in the reduction of GHG emissions into the atmosphere. Mass transit, energy-efficient buildings, and electric vehicles can be used instead of high-emission alternatives. Land use changes that increase the amount of carbon stored in soil and biomass, as well as some geoengineering techniques, constitute mitigation efforts that take carbon dioxide, CO2, out of the atmosphere. See frequently asked question, can geoengineering be used to remove carbon dioxide from the atmosphere or otherwise reverse global warming? See also Chapter 29, Mitigation. Adaptation involves policies, strategies, and technologies designed to reduce the risk of harm from climate-related impacts. Some adaptation actions are technical engineering solutions designed to address specific impacts, such as building a seawall in the face of sea level rise or breeding new crops that do well in the context of drought. Other adaptation actions involve decision-making processes, policies, or approaches that bring people together to support coordinated action. Chapter 28, Adaptation. Adaptation often involves incremental adjustments to current systems, but larger transformations may be necessary, especially as some systems cross thresholds or tipping points. Adaptation and mitigation actions can be undertaken simultaneously to reduce concentrations of GHGs in the atmosphere, while also reducing the risk of climate-related impacts. Both adaptation and mitigation can have co-benefits, societal benefits that are not necessarily related to climate change, Chapter 29, Mitigation. For example, a new coastal restoration project to plant a mangrove forest will remove CO2 from the atmosphere while providing valuable ecosystem services, a buffer against storm surges, reduced erosion, habitat for wildlife, and filtration of human pollutants. Chapter 8, Coastal. Climate resilience refers to the capacity of a human or natural system to respond to and recover from climate-related hazards, such as droughts or floods, in ways that maintain their essential or valued identity, functions, and structure. Resilient systems respond to climate stressors or impacts with less harm while also improving their ability to absorb future impacts and maintaining capacity for adaptation and learning. A resilient rural community might have the capacity to share knowledge and resources to help farmers deal with droughts while improving their ability to absorb future impacts by building long-term structures to conserve water resources. Chapter 24, Northwest. Resilience can be bolstered by diversity, such as species diversity or employment diversity. Redundancy, the ability for one part of the system to take over essential functions if another is damaged. Social networks, knowledge sharing, and good governance. Chapter 7, Ecosystems. Question: is timing important for climate mitigation? Short answer: yes. The choices made today largely determine what impacts may occur in the future. Carbon dioxide can persist in the atmosphere for a century or more, so emissions released now will still be affecting climate for years to come. The sooner greenhouse gas (GHGs) emissions are reduced, the easier it may be to limit the long-term costs and damages due to climate change. Waiting to begin reducing emissions is likely to increase the damages from climate-related extreme events, such as heat waves, droughts, wildfires, flash floods, and stronger storm surges due to higher sea levels and more powerful hurricanes. Long answer: the effect of increasing atmospheric concentrations of carbon dioxide, CO2, and other GHGs on the climate system can take decades to be fully realized. The resulting change in climate and the impacts of those changes can then persist for centuries. The longer these changes in climate continue, the greater the resulting impacts. Some systems may not be able to adapt if the change is too much or too fast. The long-term equilibrium temperature from GHG emissions will be a function of cumulative emissions over time, not the specific year-to-year emissions. Thus, staying within a specific warming target will depend on the total net emissions, including increases in carbon uptake, over a given future period. However, the timing and nature of changes are important in both reducing short-term warming and meeting any particular long-term warming limit. Long-term reductions in the rate and magnitude of global warming can be made by reducing total emissions of CO2. Near-term reductions in the rate of climate change can be made by reducing human-caused emissions of short-lived but highly potent GHGs, such as methane and hydrofluorocarbons. These pollutants remain in the atmosphere from weeks to about a decade, much shorter than CO2, but have a much greater warming influence than CO2. Figure A5.23. Question: Are there benefits to climate change? Short answer: While some climate changes currently have beneficial effects for specific sectors or regions, many studies have concluded that climate change will generally bring more negative effects than positive ones in the future. For example, current benefits of warming include longer growing seasons for agriculture, more carbon dioxide for plants, and longer ice-free periods for shipping on the Great Lakes. However, longer growing seasons, along with higher temperatures and increased carbon dioxide levels, can increase pollen production, intensifying and lengthening the allergy season. Longer ice-free periods on the Great Lakes can result in more lake-effect snowfalls. Long answer: Many analyses of this question have concluded that climate change will, on balance, bring more negative effects than positive ones in the future. This is largely because our society and infrastructure have been built for the climate of the past, and changes from those historical climate conditions impose costs and management challenges. Chapter 11, Urban. For example, while longer warm seasons may provide a temporary economic boon to coastal communities reliant on tourism, many of those same areas are vulnerable not only to sea level rise, but also to risks from ocean acidification and warmer waters that can impact the ecosystems, such as coral reefs, that bring people to the coasts. Chapter 8, Coastal. As another example, while some studies have shown that certain crops in certain regions may benefit from additional carbon dioxide, CO2, in the atmosphere, sometimes referred to as the CO2 fertilization effect, these potential gains are expected to be offset by crop stress caused by higher temperatures, worsening air quality, and strained water availability. See frequently asked question: How do higher carbon dioxide concentrations affect plant communities and crops? See also Chapter 10, Ag and Rural. Furthermore, any accrued benefits are likely to be short-lived and depreciate significantly as warming continues through the century and beyond. Question: Are some people more vulnerable to climate change than others? Short answer: Yes. Climate change affects certain people and populations differently than others. Some communities have higher exposure and sensitivity to climate-related hazards than others. Some communities have more resources to prepare for and respond to rapid change than others. Communities that have fewer resources, are underrepresented in government, live in or near deteriorating infrastructure, such as damaged levees, or lack financial safety nets, are all more vulnerable to the impacts of climate change. Long answer: Vulnerability here refers to the degree to which physical, biological, and socioeconomic systems are susceptible to and unable to cope with adverse impacts of climate change. Vulnerability encompasses sensitivity, adaptive capacity, exposure, and potential impacts. For example, older people living in cities with no air conditioning have less adaptive capacity and increased sensitivity and vulnerability to heat stress during extreme heat events. Chapter 14, Human Health. Communities that live on atolls in the Marshall Islands have high exposure and are acutely at risk to sea level rise and saltwater intrusion due to the low land height and small land area. Chapter 27, Hawaii and Pacific Islands. A history of neglect, political or otherwise, in a given neighborhood can result in dilapidated infrastructure, which, in turn, can lead to situations such as levee failures, making whole communities vulnerable to flooding and other potential impacts. Chapter 14, Human Health. Poverty can make evacuation during storm events challenging and can make rebuilding or relocating harder following an extreme event. In some indigenous communities, lack of water and sanitation systems can put people at risk during drought. Chapter 15, Tribes. Additionally, some subpopulations are already more affected by environmental exposures, such as air pollution or extreme heat. If communities or individuals experience a combination of these vulnerability factors, they are at even greater risk. Vulnerable communities and individuals face these disparities today and will likely face increased challenges in the future under a changing climate. Question: how will climate change impact economic productivity? Short answer: many impacts of climate change are expected to have negative effects on economic productivity, such as increased prices of goods and services. For example, increased exposure to extreme heat may reduce the hours some individuals are able to work. Physical capital, such as food, equipment, and property, that is derived from the production of goods and services, may be impacted because of lower production and higher costs as a result of climate change. Sea level rise, stronger storm surges, and increased heavy downpours that cause flooding can disrupt supply chains or damage properties, structures, and infrastructure that form the backbone of the nation's economy. Long answer: high temperatures and storm intensity, which are both linked to more deaths and illness, are projected to increase due to climate change, which would, in turn, increase healthcare costs for medical treatment. At the same time, these health effects directly impact labor markets. Workers in industries with the greatest exposure to weather extremes may decrease the amount of time they spend at work, while workers across a wide range of sectors may find their productivity impaired while on the job. Chapter 14, Human Health. These labor market impacts translate into lower earnings for workers and firms. Climate change is likely to affect physical capital that serves as an important input to economic production. In farming, where weather is a key determinant of agricultural yield, increasing temperatures and drought may lead to net decreases in the amount of food that farms produce. Chapter 10, Ag and Rural. Extreme heat can also cause manufacturing equipment to break down with greater frequency, while rising sea levels and increased storm intensity can destroy equipment and property across all types of economic activities along American coastlines. In addition to damaging private property, increased weather extremes can destroy vital public infrastructure, such as roads, bridges, and ports. Since this infrastructure is an integral part of supply chains that drive the American economy, a disruption in their accessibility, or even their destruction, can have large impacts on corporate profits. while their repairs require a diversion of resources away from other useful government projects or an increase in taxes to finance reconstruction. Chapter 11, Urban. Question: Can we slow climate change? Short answer: yes. While we cannot stop climate change overnight, or even over the next several decades, we can limit the amount of climate change by reducing human-caused emissions of greenhouse gases, GHGs. Even if all human-related emissions of carbon dioxide and other GHGs were to stop today, Earth's temperature would continue to rise for a number of decades and then slowly begin to decline. Ultimately, warming could be reversed by reducing the amount of GHGs in the atmosphere. The challenge in slowing or reversing climate change is finding a way to make these changes on a global scale that is technically, economically, socially, and politically viable. Long answer: the most direct way to significantly reduce the magnitude of future climate change is to reduce the global emissions of GHGs. Emissions can be reduced in many ways, and increasing the efficiency of energy use is an important component of many potential strategies. Chapter 29, Mitigation. For example, because the transportation sector accounts for about 29% of the energy used in the United States, developing and driving more efficient vehicles and changing to fuels that do not contribute significantly to GHG emissions over their lifetimes would result in fewer emissions per mile driven. A large amount of energy in the United States is also used to heat and cool buildings, so changes in building design could dramatically reduce energy use. Chapter 29, Mitigation. While there is no single approach that will solve all the challenges posed by climate change, there are many options that can reduce emissions and help prevent some of the potentially serious impacts of climate change. Figure A5.24. Question: Can geoengineering be used to remove carbon dioxide from the atmosphere or otherwise reverse global warming? Short answer: in theory, it may be possible to reverse some aspects of global warming through technological interventions called geoengineering, which can complement mitigation and adaptation. But many questions remain. Geoengineering approaches generally fall under two categories: 1. Carbon dioxide removal, and 2. Reducing the amount of the sun's energy that reaches Earth's surface. Due to uncertain costs and risks of some geoengineering approaches, more traditional mitigation actions to reduce emissions of greenhouse gases, GHGs, are generally viewed as more feasible for avoiding the worst impacts from climate change currently. However, targeted studies to determine the feasibility, costs, risks, and benefits of various geoengineering techniques could help clarify the impacts. Long answer: removal of carbon dioxide, CO2, from the atmosphere could be undertaken by applying land management methods that increase carbon storage in forests, soils, wetlands, and other terrestrial or aquatic carbon reservoirs. Trees and plants draw down CO2 from the atmosphere during photosynthesis and store it in plant structures. Reforesting large tracts of deforested lands would help reduce atmospheric concentrations of CO2. New technologies could also be used to capture CO2 either directly from the atmosphere or at the point where it is produced, such as at coal-fired power plants, and store it underground. However, CO2 removal may be costly and has long implementation times, and the removal of CO2 from the atmosphere must be essentially permanent if climate impacts are to be avoided. Solar radiation management, SRM, is an intentional effort to reduce the amount of sunlight that reaches Earth's surface by increasing the amount of sunlight reflected back to space. Since SRM does not reverse the increased concentrations of CO2 and other GHGs in the atmosphere, this approach does not address direct impacts from elevated CO2, such as damage to marine ecosystems from increasing ocean acidification. Instead, it introduces another human influence on the climate system that partially cancels some of the effects of increased GHGs in the atmosphere. SRM methods include making clouds brighter and more reflective, injecting reflective aerosol particles into the upper or lower atmosphere, or increasing the reflectivity of Earth's surface. SRM can work in conjunction with CO2 removal and other mitigation efforts and can be phased out over time. Yet, this method would require sustained costs, has not been well studied, and could have harmful, unintended consequences, such as stratospheric ozone depletion. End of section 36. Section 37 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Kearney, Illinois. Frequently asked questions. Ecological effects. Question: what causes global sea level rise? And how will it affect coastal areas in the coming century? Short answer: global sea level is rising, primarily in response to two factors. 1. Thermal expansion of ocean waters, and 2. Melting of land-based ice, both due to climate change. Thermal expansion refers to the physical expansion, or increase in volume, of water as it warms. Melting of mountain glaciers and the Antarctic and Greenland ice sheets contributes additional water to the oceans, thereby raising global average sea level. Global average sea level has risen 7 to 8 inches since 1880, and about 3 inches of that has occurred since 1993. Sea level rise will increasingly contribute to high tide flooding and intensify coastal erosion over the coming century. Long answer: at any given location, the situation is more complicated because other factors come into play. For example, coastlands are rising in some places and sinking in others due to both natural causes, such as tectonic shifts, and human activities, such as groundwater or hydrocarbon extraction. Where coastlands are rising as fast as, or faster than, sea level, relative local sea level may be unchanged or decreasing. Where coastlands are sinking, called subsidence, relative local sea level may be rising faster than the global average. Figure A5.25. See also Chapter 23, Southern Great Plains. Other variables can influence relative sea level locally, including natural climate variability patterns, for example, El Niño/La Niña events, and regional shifts in wind and ocean current patterns. Global sea level rise is already affecting the U.S. coast in many locations. Chapter 8, Coastal. High tide flooding with little or no storm effects, also referred to as nuisance, sunny day, or recurrent flooding, coastal erosion, and beach and wetland loss are all increasingly common due to decades of local relative sea level rise. Chapter 19, Southeast. Sea level is expected to continue rising at an accelerating rate this century under either a lower or higher scenario, RCP 4.5 or RCP 8.5, increasing the frequency of high tide flooding intensifying coastal erosion and beach and wetland loss, and causing greater damage to coastal properties and structures due to stronger storm surges. Chapter 18, Northeast. Chapter 8, Coastal. Relative local sea level rise projections can be visualized at https://coast.noaa.gov/digitalcoast/tools/slr.html. Question: how does global warming affect Arctic sea ice cover? Short answer: the Arctic region has warmed by about 3.6 degrees Fahrenheit since 1900, double the rate of the global temperature increase. Consequently, sea ice cover has declined significantly over the last 4 decades. In the summer and fall, sea ice area has dropped by 40%, and sea ice volume has dropped 70% relative to the 1970s and earlier. Decline in sea ice cover plays an important role in Arctic ecosystems, ultimately impacting Alaska residents. Long answer: Arctic sea ice today is in the most reduced state since satellite measurements began in the late 1970s, and the current rate of sea ice loss is also unprecedented in the observational record. Figures A5.26 and A5.27. See also Chapter 2, Climate. Arctic sea ice cover is sensitive to climate change because strong self-reinforcing cycles, positive feedbacks, are at play. As sea ice melts, more open ocean is exposed. Open ocean, a dark surface, absorbs much more sunlight than sea ice, a reflective white surface. That extra absorbed sunlight leads to more warming locally, which in turn melts more sea ice, creating a positive feedback. Chapter 2, Climate. Annual average Arctic sea ice extent has decreased between 3.5% and 4.1% per decade since the early 1980s, has become thinner by 4.3 to 7.5 feet, and has started melting earlier in the year. September sea ice extent, when the Arctic sea ice is at a minimum, has decreased by 10.7% to 15.9% per decade since the 1980s. Scientists project sea ice-free summers in the Arctic by the 2040s. Figure A5.27. See Chapter 26, Alaska. Arctic sea ice plays a vital role in Arctic ecosystems. Changes in the extent, duration, and thickness of sea ice, along with increasing ocean temperature and ocean acidity, alter the distribution of Alaska fisheries and the location of polar bears and walruses, all of which are important resources for Alaska residents, particularly coastal Native Alaska communities. Chapter 26, Alaska. Winter sea ice may keep forming in a warmer world, but it could be much reduced compared to the present. See Taylor et al. 2017 for more details. Question: is Antarctica losing ice? What about Greenland? Short answer: yes. Overall, the ice sheets of both Greenland and Antarctica, the largest areas of land-based ice on the planet, are losing ice as the atmosphere and oceans warm. This ice loss is important both as evidence that the planet is warming and because it contributes to rising sea levels. Long answer: the Antarctic ice sheet is up to 3 miles deep and contains enough water to raise sea level about 200 feet. Because Antarctica is so cold, there is little melting of the ice sheet, even in summer. However, the ice flows towards the ocean, where above freezing ocean water speeds up the melting process, which breaks the ice into free-floating icebergs, a process called calving. Melting, calving, and the flow of ice into the oceans around Antarctica, especially on the Antarctic Peninsula, have all accelerated in recent decades, and the result is that Antarctica is losing about 100 billion tons of ice per year, contributing about 0.01 inch per year to sea level rise, figure A5.28. While there has been slight growth in some parts of the Antarctic ice sheet, the gain is more than offset by ice mass loss elsewhere, especially in West Antarctica and along the Antarctic Peninsula. The West Antarctic ice sheet, which contains enough ice to raise global sea level by 10 feet, is likely to lose ice much more quickly if its ice shelves disintegrate. Additionally, warming oceans under the ice sheet are melting the areas where ice sheets go afloat in West Antarctica, exacerbating the risk of more rapid melt in the future. Greenland contains only about 1/10 as much ice as the Antarctic ice sheet. But if Greenland's ice sheet were to entirely melt, global sea level would still rise about 20 feet. For additional information on the impacts of sea level rise on the United States directly, see Chapter 8 Coastal, Chapter 18 Northeast, Chapter 19 Southeast, and Chapter 20 U.S. Caribbean. Annual surface temperatures in Greenland are warmer than Antarctica, so melting occurs over large parts of the surface of Greenland's ice sheet each summer. Greenland's melt area has increased over the past several decades. Figure A5.28. The Greenland ice sheet is presently thinning at the edges, especially in the south, and slowly thickening in the interior, increasing the steepness of the ice sheet, which has sped up the flow of ice into the ocean over the past decade. This trend will likely continue as the surrounding ocean warms. Greenland's ice loss has increased substantially in the past decade, losing ice at an average rate of about 269 billion tons per year from April 2012 to April 2016, contributing over 0.02 inch per year to sea level rise. Question: how does climate change affect mountain glaciers? Short answer: glacier retreat is one of the most important lines of evidence for global warming. Around the world, glaciers in most mountain ranges are receding at unprecedented rates. Many glaciers have disappeared altogether this century, and many more are expected to vanish within a matter of decades. Glaciers will still be around within the next century, but they will be more isolated, closer to the poles, and at higher elevations. Long answer: glaciers are critical freshwater reservoirs that slowly release water over warmer months, which helps sustain freshwater stream flows that provide drinking and irrigation water, as well as hydropower to downstream communities. However, increasing temperatures and decreasing amounts of precipitation falling as snow are major drivers of glacial retreat. See Chapter 2 Climate, Chapter 22 Northern Great Plains, Chapter 24 Northwest, Chapter 26 Alaska. Glaciers retreat when melting and evaporation outpace the accumulation of new snow. Slope, altitude, ice flow, location, and volume also contribute to the speed and extent of glacial retreat, which complicates the relationship between increasing temperature and glacial melt. Due to these local factors, not all glaciers globally are retreating. For example, melting may slow as the glaciers retreat to the upper slopes, under headwalls and steep cliffs, and into more shaded areas. In recent decades, the mountains of Glacier National Park, GNP, in Montana have experienced an increase in summer temperatures and a reduction in the winter snowpack that forms the mountain glaciers. The annual average temperature in GNP has increased by 2.4 degrees Fahrenheit since 1900. Spring and summer minimum temperatures have risen, and the percentage of precipitation that comes as rain rather than snow has increased. Mountain snowpacks now hold less water than they used to, and have begun to melt at least 2 weeks earlier in the spring. This earlier melting alters glacier stability, as well as downstream water supplies, with implications for wildlife, agriculture, and fire management. In a recent study, scientists looked at 39 glaciers in and around GNP and compared aerial photos and digital maps from 1966 to 2016. Currently, only 26 glaciers are bigger than 25 acres, the minimum size used for defining a glacier. When GNP was established early in 1910, it is estimated that there were 150 glaciers larger than 25 acres. Long-term studies of glacier size have shown that the rate of melting has fluctuated in response to decade-long climate cycles, and that the melting rate has risen steeply since about 1980. Over the next 30 years, glaciologists project that most glaciers in GNP will melt to a point where they are too small to be active glaciers, and some may disappear completely. All glaciers in the park are under severe threat of completely melting by the end of the century. Question: how are the oceans affected by climate change? Short answer: the oceans have absorbed over 90% of the excess heat energy and more than 25% of the carbon dioxide, CO2, that is trapped in the atmosphere as a result of human-produced greenhouse gases, GHGs. Due to this increase in GHGs in the atmosphere, all ocean basins are warming and experiencing changes in their circulation and seawater chemistry, all of which alter ecosystem structure and marine biodiversity. Long answer: the world's oceans have been and will continue to be impacted by climate change. More than 50% of the world's marine ecosystems are already exposed to conditions, temperature, oxygen, salinity, and pH, that are outside the normal range of natural climate variability, and this percentage will rise as the planet warms. Chapter 9, Oceans. Global warming will alter the ability of species to survive, and can reorganize ecosystems, creating novel habitats and/or reducing biodiversity. Some species are responding to increased ocean temperatures by shifting their geographic ranges, generally to higher latitudes, or altering the timing of life stages, for example spawning, figure A5.29, see Chapter 7 Ecosystems, Chapter 18 Northeast. Other species are unable to adapt as their habitats deteriorate, for example due to loss of sea ice, or the rate of climate-related changes occurs faster than they can move, for example in the case of sessile organisms such as oysters and corals. Physical changes to the ocean system will also occur. Observations and projections suggest that in the next 100 years, the Gulf Stream, part of the larger ocean conveyor belt, could slow down as a result of climate change, which could increase regional sea level rise and alter weather patterns along the U.S. East Coast. In addition to causing changes in temperature, precipitation, and circulation, increasing atmospheric levels of CO2 have a direct effect on ocean chemistry. The oceans currently absorb about a quarter of the 10 billion tons of CO2 emitted to the atmosphere by human activities every year. Dissolved CO2 reacts with seawater to make it more acidic. This acidification impacts marine life, such as shellfish and corals, making it more difficult for these calcifying animals to make their hard external structures. Chapter 8, Oceans. Chapter 24, Northwest. Over the last 50 years, inland seas, estuaries, and coastal and open oceans have all experienced major oxygen losses. A warmer ocean holds less oxygen. Warming also changes the physical mixing of ocean waters, for example, upwelling and circulation, and can interact with other human-induced changes. For example, fertilizer runoff entering the Gulf of Mexico through the Mississippi River can stimulate harmful algal blooms. These blooms eventually decay, creating large dead zones of water with very low oxygen, where animals cannot survive. Warmer conditions slow down the rate at which this oxygen can be replaced, exacerbating the impact of the dead zone. These are just a few of the changes projected to occur, as detailed in Chapter 9, Oceans. Question: what is ocean acidification, and how does it affect marine life? Short answer: the oceans currently absorb more than a quarter of the 10 billion tons of carbon dioxide, CO2, released annually into the atmosphere from human activities. CO2 reacts with seawater to form carbonic acid. So, more dissolved CO2 increases the acidity of ocean waters. When seawater reaches a certain acidity, it eats away at, or corrodes, the shells and skeletons made by shellfish, corals, and other species, or impedes the ability of organisms to grow them in the first place. Long answer: since the beginning of the Industrial Revolution, the acidity of surface ocean waters has increased approximately 30%. The oceans will continue to absorb CO2 produced by human activities, causing acidity to rise further. Figure A5.30. Ocean waters are not acidifying at the same rate around the globe, largely due to differences in ocean temperature. Warmer, low-latitude waters naturally hold less CO2 and therefore tend to be less acidic. Colder, high-latitude waters naturally hold more CO2, have increased acidity, and are closer to the threshold, where shells and skeletons tend to corrode. Coastal and estuarine waters are also acidified by local phenomena, such as freshwater runoff from land, nutrient pollution, and upwelling. In the past 5 years, scientists have found that the shells of small planktonic snails, called pteropods, are already partially dissolved in locations where ocean acidification has made ocean waters corrosive, such as in the Pacific Northwest and near Antarctica. Pteropods are an important food source for Pacific salmon, so impacts to pteropods could cause changes up the food chain. Acidification has also affected commercial oyster hatcheries in the Pacific Northwest, where acidified waters impaired the growth and survival of oyster larvae. Chapter 24, Northwest. Because marine species vary in their sensitivity to ocean acidification, scientists expect some species to decline and others to increase in abundance in response to this environmental change. Relative changes in species performance can ripple through the food web, reorganizing ecosystems as the balance between predators and prey shifts and habitat-forming species increase or decline. Habitat-forming species, such as corals and oysters, that grow by using minerals from the seawater to build mass, are particularly vulnerable. It is difficult to predict exactly how ocean acidification will change ecosystems. Scientists and managers are now using computer models to project potential consequences to fisheries, protected species, and habitats. See Chapter 9, Oceans, for more details. Question: how do higher carbon dioxide concentrations affect plant communities and crops? Short answer: plant communities and crops respond to higher atmospheric carbon dioxide concentrations in multiple ways. Some plant species are more responsive to changes in carbon dioxide than others, which makes projecting changes difficult at the plant community level. For approximately 95% of all plant species, an increase in carbon dioxide represents an increase in a necessary resource and could stimulate growth. Assuming other factors like water and nutrients are not limiting, and temperatures remain in a suitable growing range. Long answer: along with water, nutrients, and sunlight, carbon dioxide, CO2, is one of 4 resources necessary for plants to grow. At the level of a single plant, all else being equal, an increase in CO2 will tend to accelerate growth because of accelerated photosynthesis. But a plant's ability to respond to increased CO2 may be limited by soil nutrients. Exactly how much growth stimulation will occur varies significantly from species to species. However, the interaction between plants and their surrounding environment complicates the relationship. As CO2 increases, some species may respond to a higher degree and become more competitive, which may lead to changes in plant community composition. For example, loblolly pine and poison ivy both grow in response to elevated CO2. However, poison ivy responds more and becomes more competitive. The expected effects of increased CO2 in agricultural plants are in line with these same patterns. Some crops that are not experiencing stresses from nutrients, water, or biotic stresses such as pests and disease are expected to benefit from CO2 increases in terms of growth. However, the quality of those crops can suffer, as rising levels of atmospheric CO2 can decrease dietary iron and other micronutrients. Chapter 14, Human Health. Plants often become less water-stressed as CO2 levels increase because high atmospheric CO2 allows plants to photosynthesize with lower water losses and higher water use efficiencies. The magnitude of the effect varies greatly from crop to crop. However, for many crops in most U.S. regions, the benefits will likely be mostly or completely offset by increased stresses, such as higher temperatures, worsening air quality, and decreased ground moisture. Chapter 10, Ag and Rural. If crops and weeds are competing, then rising CO2, in general, is more likely to stimulate the weed than the crop, with negative effects on production unless weeds are controlled. Controlling weeds, however, is slightly more difficult, as rising CO2 can reduce the efficacy of herbicides through enhanced gene transfer between crops and weedy relatives. Downstream impacts of rising CO2 on plants can be significant. Increasing CO2 concentrations provide an opportunity for cultivators to select plants that can exploit the higher CO2 conditions and convert it to additional seed yield. However, an area of emerging science suggests that rising CO2 can reduce the nutritional quality, protein and micronutrients, of major crops. In addition, rising CO2 can reduce the protein concentration of pollen sources for bees. Climate change also influences the amount and timing of pollen production. Increased CO2 and temperature are correlated with earlier and greater pollen production and a longer allergy season. Chapter 13, Air Quality. Please see Chapter 10, Ag and Rural, Chapter 6, Forests, and Ziska et al. 2016 for more information on how climate change affects crops and plants. Question: Is climate change affecting U.S. wildfires? Short answer: It is difficult to determine how much of a role climate change has played in affecting recent wildfire activity in the United States. However, climate is generally considered to be a major driver of wildfire area burned. Over the last century, wildfire area burned in the mountainous areas of the western United States was greater during periods of low precipitation, drought, and high temperatures. Increased temperatures and drought severity with climate change will likely lead to increased fire area burned in fire-prone regions of the United States. Long answer: Climate is a major determinant of vegetation composition and productivity, which directly affect the type, amount, and structure of fuel available for fires. Climate also affects fuel moisture and the length of the season when fires are likely. Higher temperatures and lower precipitation result in lower fuel moisture, making fire spread more likely when an ignition occurs, if fuel is available. In mountainous areas, higher temperatures, lower snowpack, and earlier snow melt lead to a longer fire season, lower fuel moisture, and higher likelihood of large fires. Forest management practices are also a factor in determining the likelihood of ignition, as well as fire duration, extent, and intensity. Chapter 6, Forests. Long records of fire, provided by tree ring and charcoal evidence, show that climate is the primary driver of fire on timescales ranging from years to millennia. During the 20th century in the western United States, warm and dry conditions in spring and summer generally led to greater area burned in most places, particularly more mountainous and northerly locations. Figure A5.31. The frequency of large forest fires, greater than 990 acres, has increased since the 1970s in the Northwest 1,000%, and northern Rocky Mountains 889%, followed by forests in the Southwest 462%, southern Rocky Mountains 274%, and Sierra Nevada 256%. Dry forests in these regions account for about half of the total forest area burned since 1984. Globally, the length of the fire season, the time of year when climate and weather conditions are conducive to fire, has increased by 19% between 1979 and 2013, and it has become significantly longer over this period in most of the United States. With climate change, higher temperatures and more severe drought will likely lead to increased area burned in many ecosystems of the western and southeastern United States. By the mid-21st century, annual area burned is expected to increase 200% to 300% in the contiguous western United States and 30% in the southeastern United States. Over time, warmer temperatures and increased area burned can alter vegetation composition and productivity, which, in turn, affect fire occurrence. In arid regions, vegetation productivity may decrease sufficiently that fire will become less frequent. In other regions, climate may become less of a limiting factor for fire, and fuels may become more important in determining fire severity and extent. In a warmer climate, wildfire is expected to be a catalyst for ecosystem change in all fire-prone ecosystems. Question: Does climate change increase the spread of mosquitoes or ticks? Short answer: yes. Climate change can contribute to the spread of mosquitoes and ticks. A warmer climate enhances the suitability of habitats that were formerly too cold to support mosquito and tick populations, thus allowing these vectors and the diseases they transmit to invade new areas. Long answer: mosquitoes and ticks are dependent on external sources for body heat. Thus, they develop from egg to adult more quickly under warmer conditions, producing more generations in a shorter time. Warming also speeds up population growth of the parasites and pathogens that mosquitoes transmit, including the agents of Zika virus, dengue fever, West Nile virus, and malaria, as well as the rate at which mosquitoes bite people and other hosts. Additionally, warmer conditions facilitate the spread of mosquitoes by increasing the length of the growing season and by decreasing the likelihood of winter die-offs due to extreme cold. Chapter 14, Human Health. Black-legged deer ticks are the main vector or transmitter of Lyme disease in the United States. These ticks require a minimum number of days above freezing to persist. As a result, some northern and high elevation areas cannot be invaded because the warm season is too short to allow each life stage to find an animal host before it needs to retreat underground. But as higher latitude and higher altitude areas continue to warm, black-legged ticks may expand their range northward and higher in elevation. Figure A5.32. See also Chapter 14, Human Health. Studies show that ticks emerge earlier in the spring under warmer conditions, suggesting that the main Lyme disease season will move earlier in the spring. Thus, earlier onset of warm spring conditions and warm summers and falls increase the establishment and resilience of tick populations. End of section 37. End of 4th National Climate Assessment, Volume 2, Impacts, Risks, and Adaptation in the United States by USGCRP.